Hello everyone, nice to see you again. As I promised, we're always going to meet on the first Saturday of each month. So the link for the stream, you can find it in the description on YouTube. Click on that link so you can join the stream, and especially if you have any questions that you want to ask or any discussion. So my colleague Bilal Hussein today, he's going to be a bit late, but I'll probably start the stream unless someone would like to join. Today I would like to actually talk about the RZ geometry. Last time we have presented the user code, and this is another user code that's available from EGSnrc. And the RZ geometry, from its name, it's basically sets up a phantom with an R and Z, defined by R and Z, cylindrical symmetry. And there are various user codes that are used to calculate quantities of interest. For example, there is a dosrznrc user code. Another one is sprrznrc and fluorznrc and cavrznrc. Dosrznrc is probably the most commonly used user code. sprrz is also another commonly used code. Personally, I haven't used cavrz in any of my work, but dosrz is probably the one that I've used the most. Why there is another code, user code is the dosxyznrc, and in that user code, one gets to calculate the dose in an x and y, xyz geometry, whereas dosrz, the calculation is in an rz geometry. So why this code is different? Why that's the useful? Why this code is useful? This code runs very fast. It's much faster to run than the dosxyz NRC code. And it's useful, of course, if you want to calculate things along the central axis. Anything off axis, probably I wouldn't recommend using the RZ code, but anything along the central axis, or whenever you have a cylindrical symmetry, it's better to use this code than the dosxyz. It's faster to actually execute. So let's dig in, and let's go and look at this user code. And again, if you want to just join me on the stream, just click on the link on the description of this video. Okay. So this is okay, I have things running on Ubuntu, Linux. To access the EGSnrc codes, there is a shortcut here, EGS input RZ. And if you open this shortcut, we find these are the user codes that I was talking about. cavrz, dosrz, sprrz, fluorz. Dosrz is used to calculate doses. sprrz is to calculate second power ratios. fluorz is for fluence. And finally, cavrz is a user code that's specifically for cylindrical ion chambers to calculate some quantities of it. So we'll begin with the dosrz code. And the first, so this is selected. So the user area code area. This is by default is going to be in the home area home, and the text data could be either in the hen house, or if you have actually made your own text data, then probably that is going to be under the eggs home. The next thing we need to do is to give the input file a name. So today I'm going to demonstrate several things. So let's calculate, for example, a depth dose, percentage depth dose along the beam central axis for coder. So I'm going to call this depth dose, and I like to make the name meaningful, so it's easier, you know, to note the input file, what's the calculation, so on. This is the text data file. These are the files now that are listed in the hen house area. If, for example, I selected the X home, then I will have different types of the files in that area. So I don't know. I'm gonna use this file, and then the best thing is whenever these are the tabs for the input file, and my suggestion is whenever you finish modifying something in one of these tabs, just save. Okay? So we're going to save. By the way, if you've just installed EGS, then probably you will not get execute will not be enabled. The reason is probably the dosrznrc might not be compiled. All what you need to do is just to compile it, close this application, open it, and then you will find you can now execute the code. So we'll go move on to the next tab. Here, nothing really to change except the iris start. So first is obviously when this is the first time you're running a simulation. Restart if you want to accumulate more histories of the results. iWatch, this is something you should not be worried about. This is for application. I forgot what it's called. It's called X. I forgot. But that used to be an application that can display the geometry nicely and the history of particles also. It's called EGS Windows. That's the application. So we'll move to the next tab here, Monte Carlo. Here we have, these are the number of histories. My recommendation is always to start with something small, just to make sure that the application runs. The maximum CPU time allowed, probably if it's a new application, this will be 90. I have it set to 500, that's the maximum value. And statistical accuracy sort is 0. Basically, one can set a value here, and the simulation is going to run and will be stopped by one of these parameters, whichever is reached first. So if the application now completes 100,000 histories, it's going to stop. If the CPU calculation time exceeds 500, then it's going to be stopped. And if the statistical uncertainty sort is less than 0, which is basically that's the maximum. But for example, if we put this to be 0.2, then if the statistical uncertainty in the calculation is less than 0.2, then it's going to be stopped. I usually leave this to 0, and the maximum CPU, I'll make it maximum, and I control everything using the number of histories. This is here if you want to score kernel. I'm interested in those, not in kernel at this time. So I will leave this. I will not click this. Then we can save. We can save. Yes, override geometry. So the geometry, this is an RZ geometry. I want to have this is cobalt. So I'm going to use the groups method, and I'm going to put let's say 10 slabs of 0.2 0.1. So this is the total BM. And then let's do another 10 slabs. And it is at 0.2. So this is now 3 cm. I think I have a total of 61. That's the default with the those I think, unless one changes parameters that we compile the code, but I think it's about, I think 61 if I'm not mistaken. And then we go to 0.5. So this is 1 centimeter, 2 centimeters, but it's 3, and here I have 5, 8. So we're going to go now, it's 1, and another 10, 2 centimeters. Okay, so I think I have more than 30 centimeters. You can play with this, define thicknesses the way you wish. I like to have finer definition of thickness, obviously in the build-up region, and then the rest, I guess, increase the slab thicknesses as different also. But you can do, you can have a different way of defining your depth. That's not a problem. Now, in the cylinder part, so a radius of 1, so this is the inner cylinder. The radius, you can leave it at 1, and then I just need here 30, and I try to make these again equal. So basically, I have an inner cylinder with a radius of 1 cm, and then surrounded by a ring that goes from 1 cm from the center up to 30 cm. And so I have, now we need to define, put the media there. So I have a total of 50 slides, and here, so I can just select 50. And this one, we don't need actually. I don't know how to remove, there is a bug in this user interface, at least for the Linux version. I don't know how to remove the second entry. I can always go and remove it from the input file, the text editor. So I'm going to leave it like this, and let's save. My suggestion also, once you enter these parameters that define the geometry, you can preview it using preview object. You just have to save first, and now we can preview the geometry. And let's put this to be 80. Okay. So these are the slabs. So this is an RZ geometry. This is a cylinder. Okay. And the radius here, I think it's for that we use 1 cm, and then the other one reaches 30 cm. But the slabs thicknesses, these are 10 slabs with thickness of 0.1, and then we have another 10 with thickness of 0.2, and so on. Remember, the doses are representative of the dose. We usually assign it to the center of the geometry, center of the slab. So in this case, I cannot get, for example, dose at 0, but it's actually going to be at 0.05. That's the minimum dose. If I want to get a dose at closer to the surface, then we need to make the first slab thinner. Of course, that means that calculation time to get a reasonable uncertainty of the dose in that slab is probably going to require a lot of calculation time. Okay, so we're going to save. Then the next step is we go to the source. This is a parallel beam from the front. The radius is 5, which is fine. I'm going to leave this default. So you can imagine the front, and then the beam is coming from top to bottom. This is why we have this angle WNC. More details you can find in the manual and different source numbers and how to use them. Incident particle, although we can actually select the spectrum, and there is a global 60 spectrum. And I believe this spectrum, this is okay. There is a global 60 and there is another global 60. One of them is probably for from a therapy machine, and that's usually what we are interested in more when we do simulations with external beam. But I'm not sure which one is which. So I'm going to say, yes, and select this one. So global 61 is more. I really don't know which one is which, so I'm going to select the global 60 spectrum. But you could leave it at 1.25. That's not a problem. Depends on how accurately you want to represent your source. I mean, we're talking about an external beam therapy source here. So obviously the source emits the two gammas, but what reaches the phantom could there will be some scattering photons with lower energy. So we're going to save and transport parameters. This is where we control the physics. The most important thing is your electron step algorithm should be +2, boundary crossing algorithm exact, and the spin effects should be the rest are not that important, well, at least for our mega voltage simulations here. But I personally like to actually just use the high-end physics. So I don't like the word simple. I'll go and select and here use this. And what else? We could change. You don't need to worry about these numbers. Well, the global ECAT, that's 10 keV here. 10 keV for photons, that's fine. Radio scattering, that's on. Photoelectric sampling on. Atomic relaxations on. Bound content, let's put that on. And that's it. Okay. So now we can save. And then various reduction techniques. We're not going to use any of these various reduction techniques now, but I'm going to show another example where maybe we could use the floating cross-section here for airport. Okay, so I'm going to leave this and this. Okay, and then the plot control. So the plotting, I usually like to do points, point plot. You can do both. And this is where we control what needs to be plotted. So radial, so IX is a plot that is depth in radial region. Remember, we have two radial regions. One is at the center, and then the other one is between 1 and 30. So we don't need this one. One is the first region. And planar, I'm not interested in any planar plots. Let's see if we'll accept what I've done so far. So once we save, we can execute and run the simulation. Unsuccessful output value sort plot planar. Okay, it requires probably a planar. Okay, so then I'm keeping that slab. That's the 10th slab. It will plot 2 points. Let's save and execute again. Done. So now it's running. This simulation is running now. Okay, finished. Okay. So the simulation finished running, execution. Question now is how can we look at that? We can do this from 2 different locations. The first location is we will go to our home area into the goals. I just want to check if someone entered the stream. It's okay, I don't see anyone. Okay, that is Hassan. Okay, let's try. Okay, Hassan, I see you entered the stream. If you turn on the mic, then I can add you, and then we can have a discussion. Okay, I'll return back until you fix my issue. Okay, so we'll go to dosrznrc. Let's see. And we will look into one output file called 60 and that. So the EGS list is a file, it's a text file that has the output of the simulation. Okay, first, this is what has been used in the simulation, and the number of histories, and this is the spectrum that was used. And it seems to me that it is, yes, it's probably for a teletherapy machine, because I can see here, this is almost like 50%, 50%, these are the two gammas. But there is some influence spectrum from the smaller energies. So I think this is for a teletherapy machine. Okay. So if we continue, now we're getting, this is how they used to do it probably in the past. We're getting in the text field, the text file, the geometry that we have used. So these are the, this represents a disk, and this is a ring. Surrounding this disk and a disk. And just lists the mass of the material in that geometry. Okay. And if we go further down, now here, it lists actually in these the geometries, in these regions, what is the total dose per incident influence, and what is, I think it's the primary dose. So this is primary, and this is the total. So if you want to get the scattered dose from scatter, then it's subtracted to. Of course, in this definition, scattered dose is those deposits from photons scattered within the phantom. We're not talking about the lunar active or the teletherapy head. Usually, any photon reaches, although it could be actually generated from a scattering event within the treatment head, when it comes to the phantom, that is a primary photon. So the scattering here, the scattering dose is actually from photons scattered within the phantom. And you can go and just list these numbers to define the dose. So here it will be the dose at 1.5. It will actually be 6 point something, 10 to the power minus 12 per incident influence. So it's per particle or incident influence. There is another way, another one. It's 60, and then if you do a dash, then it's the VG pop. Okay, this is exactly the same results. Here it's showing the depth at the center of the slab. This is the dose, the influence. There is influence, and this is the uncertainty on the dose. And this format is, it's ready to be shown by some rates and limits or in windows, we can actually open this, and there is our okay. Of course, here it's noisy. We need to run more simulations, and just understand that roughly to decrease the uncertainty by half, as a rule of thumb, you probably need to simulate uh, fourfold the number of particles. So, for example, if I want to decrease the uncertainties here by one half, then I would need to simulate 400,000 histories approximately. Or let's do that. So I can show you this option. So we can go back to the transport. It's in the first one. Remember, there it is. There's the input-output control. And instead of first, then I'm going to change this to start. And in the Monte Carlo, I'm going to add 300,000 more histories. And you have to save first, and then you will execute. Okay. While this executes, I'm going to check if someone is in the stream. Okay, Sam left the stream. Okay. So here we can see that it's restarting input file, 300,000 new plus 100,000 old. And let's quickly look at this. So notice that the values did not change roughly. This is, I often find this is a misconcept, and many people ask me questions. I want to model, for example, the dose from 1 minute of the COVID, or an activity, source activity of, let's say, 10,000 queries. How to do that? Well, Monte Carlo, first that is going to take you a lot of time. Uh, just to simulate the disintegrations and get the dose from there. But the way this works is Monte Carlo is it records calculates the dose per history, and you run history as many histories as you wish until the uncertainty is acceptable, and then so basically you're calculating the dose per disintegration. Then, if you want to calculate what's the dose per an activity source, then you just multiply by the activity of the source. That gives you the dose. Here in this case, this is dose per influence. This is influence. It's not really per disintegration from the COVID source. It's from incident. It's basically dose per incident influence. So it's a bit different. But what I want to emphasize on is that don't think of, for example, Monte Carlo. Think of, for example, how many disintegrations are happening in the source. Or, for example, in case of a LINAC beam, the current that is hitting the target, how much is that current? And if you just do a simple calculation, you'll find out that it's going to take a lot of time just to calculate the dose from a single pulse hitting the target, let alone for, let's say, 100 monitor units. So that doesn't work that way. Okay, so the next step is, think about it. Why would, for example, I want to simulate the dose from PDT from a COVID beam? This is something that I can easily measure And I get often, this question, what do I use for Monte Carlo for? Well, you can use Monte Carlo to simulate a measurement that you're going to do. But I think what's the more interesting part is to simulate an experiment of a measurement that you cannot do. It's a bit difficult to do. And in that case, what you need to do is you need to make sure that the Monte Carlo model you're using, for example, the beam and so on, is valid. And we do that by validating or checking the results against measurements that we've done. Once you have validated that the Monte Carlo predicts the measurements, then we can probably use that source to calculate things that we cannot measure. Okay, let me give you a few examples. So I'm going to close. And okay, so Faisal, you will need to enable your mic if you want to join me on this stream. Okay, let's share another thing. Okay, this is another example. This is where I want to share with you how to, let's look at the example again. Okay. This is a schematics of a chamber. Suppose that we designed a parallel plate chamber and we have a material, I'm going to assume it's PMMA, so it's a plastic material. The reason I'm selecting PMMA because I have that material in my mixed data file. And then we have, obviously this is cylindrical symmetry. So we have the polarizing electrode here, polarizing electrode with a thickness of 0.5 millimeter. That's made out of graphite. There is an entrance window of 1 millimeter for the chamber. So all of this, the gray material is PMMA. This is graphite or carbon, thickness of 0.5 millimeters. And we have air inside the chamber of thickness between the two electrodes is 2 millimeters. Then we have at the bottom, we have the collecting electrode here. It has a radius of 5 millimeters or a diameter of 10 millimeters. And then we have a dark ring surrounding the collecting electrode with a width of 2 centimeters. So let's try first to put this geometry in the RZ geometry, in the RZ and what I want to do is what I want to do now is, hello? Hello there. Okay, I haven't been on left. Okay, we'll continue. So let me open again. So let's, or maybe just let me tell you what I want to do exactly. I want to calculate the KQ for this chamber. Calibration of external beam. There is an ND factor for the chamber that's usually established in a covered beam and provided from a standards level, primary standards dosimetric lab, or a secondary, at a dosimetry secondary lab, ADCL. And if you want to use that chamber with a different beam, then probably you will need a correction factor, because the calibration factor was established usually for code. And that correction factor is commonly called the KQ factor, or TRS they call it KQ0 factor, something like this. So how do we calculate, how can we establish that factor for a chamber? So what we need to do is we need to first calculate the dose and or the response, the NDW, the ND for that chamber with Monte Carlo, or it could be measured actually, that's how it's established. And then we take exactly the same geometry into the beam that of our interest, and we repeat the calculation. And if we divide the two equations, we will get that the KQ is just going to be equal to the ratio of the doses in water for the two beams at the same depth, divided by the ratio of the charges that are charges in the chamber. That is roughly, in a nutshell, that's what we do. So let's see how can we do this with Monte Carlo. We don't have to. We're not going to measure anything, but we're going to actually simulate the chamber. So let me change the title. I'm going to call this parallel chamber forward. So we have a depth dose there where we can establish the dose at a given depth, let's say in the phantom, in water. But now I want to do the chamber, so PP chamber, and I'll put this as forward. Okay, so let's save. Then the next step, we go to the input output control. I'm going to put this as first, and fine, 100,000 at the beginning. And now we come to the geometry. Okay? So we want to remove these. So we want to position this chamber at 10 centimeter depth. And for a parallel chamber, the point of measurement is below the entrance window, or in our case, below the polarizing electrode. By the way, the thickness of 0.5 millimeter is a bit large. It's usually about 30 to 50 micrometers. But I'm using 0.5 for the electrodes just so that it's visible. It's going to be visible in the geometry that we're using. So we need to put the point above the reference, above the polarizing electrode at 10 centimeter depth. The entrance window thickness is 1 millimeter and the polarizing electrode thickness is 0.5 millimeter. So we need to put water above the chamber of thickness of 9.8. So we have one slab, and its thickness is 9.85. Then we have the second slab that will represent the thickness of the entrance window. It was 1 millimeter. So I have 1, and this will be 0.01, sorry, 0.1 here. And we have the electrode thickness. This is 0.05. And then we have air in between, that is 2 millimeters. And then we have electrodes with thickness again, which is 0.05. And at the bottom, below the chamber, I think it was 5 millimeters. And then we have water below this, and then it's 30 centimeters. So this is for the slabs of that geometry. Now we come to the radius. So we have 0.5. That's because the diameter of the collecting electrode was 10 millimeter. So the radius is 0.5. And then the outer electrode, the guard electrode goes to a distance of 2.5. So this will be at 2.5. Then we have a side thickness of the chamber of 2 millimeters. So this is going to be at 2.7. And then we have water outside this. I'm going to put that here. Now we're going to fill the geometry. So the best thing is first I'm going to fill everything with water. So I have 1, 2, 3, 4, 5, 6, 7 slabs. So 1 to 7. And then I have 1, 2, 3, 4. So this, the first line will fill everything with water. Then I want to replace part of that water. So let's replace the chamber, the PMMA. Let's hope that I have it here, PMMA. Okay. And that will be from the second slab up to 6. And yeah, from 2, 3, 4, 5, 6. And from inner, we have from 1, 2, 3. So this will go from 1 to 3. I understand this is a bit tricky to most of the beginners, but as you get to write these geometries, you will understand what's going on here. And then we have carbon. Okay, so that will be the graphite. So this will start from 3 up to 5, and then this will be 1, 2, and then we have air in the center. Don't worry about these things. Okay, but so 4, 4, and then we have 1, 2. This should do it. So let's check our geometry, and let's preview it. So it will be 80. So this is water, and I want actually the minimum value, number of ticks at region boundaries. Yes, this is what I want. Okay. Let me increase this to 1.2. So now you're getting to see what's going on, and then I can replace this material. So let's put it black. Okay. So now this is how it looks like. We have air in the middle, and you see below the electrode, it's going to start at 10 centimeter. So this will give me the dose at 10 centimeter. Or that's the effective point of measurement. So the dose in Monte Carlo is actually going to be reported at 10.1, because this thickness is 2. But that point, that dose in phantom, represents the dose at 10 centimeter, because the effective point of measurement is below this window. So you can see the chamber, the design, this is PMA, and so on. So the equation for the dose is going to equal to the charge multiplied by ND for the chamber. Well, the dose is something, yes, that's the dose in water at 10 centimeters. That is what we're going to get from the depth dose curve that we previously ran. So we need to go and check what is the dose at 10 centimeters. The dose or the charge in the chamber, this is basically the dose in this region here. I'm going to assume that this is a perfect chamber. The guard electrodes are really well defined in the conduction volume of the ions. So the dose or the charge within the air in this region here, that is actually the charge that is the Q. That's the dosimetric signal. But in Monte Carlo, we get a dose. We don't get a charge. So how do we convert this to charge? Well, first, we multiply the dose by the volume and the density, or basically multiply the dose by the mass. That's the whole idea. Okay? So we have the volume, we have the mass, then we can multiply or the density. And actually, and we're going to see it actually gives us the mass of this region. So we just multiply the dose by that mass. That gives me the energy deposited in this region. To convert that to charge, the W over E value, roughly it's 33.97 joules per coulomb. So basically, we need 33.97 joules to get 1 coulomb of charge. So we can convert this dose to charge. The dose in water divided by this charge gives me the NDW. Okay? But that quantity, honestly, is usually measured because it's very difficult to actually be sure of the definition of the volume of charge conduction. But I'm going to assume that, okay, we can control that and measure it and get it from this multi-time simulation. Again, the source, I'm going to leave everything the same, cobalt, the spectrum, the same radius, beam, and here is something that maybe you want to actually, because now we're interested, I'm not interested in this simulation to get the dose everywhere in these regions. I'm interested to get the dose in one particular region, that is in the air region. Okay? I'm interested in getting the dose there. So one thing we could do is actually enhance, because that is air, we can enhance the cross-section factor, because photons will just be passing through that region, not interacting. You're not going to get, we need to do a lot of simulations to get the dose represent uncertainty in that way. But a way to apply a variance reduction technique is to enhance the cross-section factor. So let's look at the geometry. Probably we want to enhance the factor in this geometry here, 4412. So let's see, I've never used it before, but this is the start. Oh, these are in regions. Okay, I'm going to show you what they mean by regions. It's not like that. So I'm going to leave this to be run and make sure everything is fine. I'm going to leave this the same. And let's save. And let's execute. Hope there are no errors. No errors. It's just executing. Okay. We can go now and look into the more effectively and further. It is the 5. It's 5. Okay. So the first thing is I want this geometry, and in particular, I want this number here. Okay, because that is the mass. This is air. So just imagine you have water, you have MMA, you have graphite, and then we have the air. So this represents actually the the air collection volume. So that's the mass of that volume. Now here, this is the regions. So we can see this is the region number 5, and this region is 12. Okay? So here is air and here is air. So what we need to do is to we can you know if you're interested to use the variance reduction technique by increasing the cross sections for air, then we need to do it for region 5 and region 12. So we can go back. So we can go and do it from here. So this is region 5, and we want this region 12. And the enhancement factor, I'm going to put 1000. So air now has probably the same probability of interactions like water. Okay. And remember, the dose is going to be scaled down, or whatever particle things will be scaled down by 1,000 by this enhancement factor. So there is nothing, it's not going to be, you're not going to get like 1,000 times dose or something like this. So let's save. Okay. And let's look at the dose. And we are, so this is the dose. We are interested in the dose in this region. It's 2.7, 25 minus 10, there is influence, but this uncertainty is 51%. Okay? So let's see with this, what we have done. Can we reach and reduce this uncertainty? Of course, to reduce it, we just need to run more simulations. But let's rerun the simulation, but with the same number of histories and see what is the uncertainty. Is it better? To be honest, I haven't used this, but I know some people have used that. So variance reduction technique, we have that's there, and let's save, and let's execute. So I'm assuming that this second run, the same number of histories, it's with a variance reduction technique perception enhancement. So let's okay, obviously the mass is going to be the same. But let's see, okay, well, it seems it did not do anything because I'm seeing 53%. It's probably something I don't know how to use it properly. Probably that's the reason. This, or maybe it's selected the wrong region. But I thought it's 5 and 12. Anyway, this shows you the results. I'm not interested in the dose in any other region except for here, because this region gives me I can calculate what is the Q for the simulation. Okay. Let's go back. share again. So this is the equation that I was just talking about. We have the dose in water equals to charge times NDW. Theoretically, yes, we can calculate actually the NDW with Monte Carlo. The only problem is usually this is not accurate because this requires that we define the collection volume, and usually it's very difficult to define that collection volume, at least for commercial, commercial available chambers. So this is the general equation. We have the dose, we have the charge, and NDW. Now, for a different energy other than cobalt, then this is NDW for cobalt, and we multiply this NDW by a convection factor for the beam of interest. This could be a photon, could be an electron beam. And the dose then in the water for that beam and that depth equals to the charge conducted multiplied by the NDW, cobalt, and the liquid. So if we multiply, or let me integrate copy paste. So for cobalt, we don't have this. And this is the reference. Okay. So this is the dose in cobalt, this is the charge, and maybe we should actually just put here again to understand what's going on. Or actually, I think it's M, transfer limitation with TRS. Okay. And it's M. Okay, and this is for our beam, quality Q. This is the dose. Okay, so this is the dose in water for beam quality Q equals to the charge. Okay. Obtained at that energy multiplied by the NTW for cobalt, that's the reference beam, multiplied by this Q. So if we divide this by this, then what do we get? We get the NDWs, they will cancel out, and we have a ratio of doses, we have the ratio of charges, and then we have the easier, let's put this above that. Okay. So again, KQ is going to be equal to the ratio of the doses divided by the ratio of the charges. So these can come back. The doses with Monte Carlo, we can calculate as long as I have a beam, okay? And the charges we can calculate. Okay? And we can, basically, once I have these values calculated, we can then estimate and get our KQ. One thing you have to be careful with is usually, I think in practice, things are done with, I mean, you could actually claim that if you can measure these quantities, you don't need Monte Carlo, and that is true. So if, for example, in a standards lab, you can measure the dose accurately for a particular beam, usually with the variability, and I think it's available, then you can start, then just put the chamber. You have a dose in water for cobalt and dose for that beam. Take the charges, and using this equation you can calculate. But since we don't have access to a standards lab, then this is another way to estimate using Monte Carlo what is the KQ. And of course, we have to run the simulations until we get a reasonable uncertainty on this KQ. I think the current, usually it's the uncertainty that is around 1%. on the plate heat. So that would require a lot of simulations, especially because of the dose in or the charge of the dose in air. That would require having a good machine for a lot of installation. So this is an application that I thought to show you. Mr. Rahman? Yes? I was trying to get someone else to, someone in the stream to maybe have some questions. So I hope today I managed to at least talk about the dosrznrc code, some of the applications that you can use the dose for, the code for. Uh, uh, there are much more stuff. I think you can actually estimate the response of detectors and so on with the code. I will not go into it. I don't have a lot of experience in that. But another thing is, remember with Monte Carlo, yes, it's fun to actually use it to calculate things that you could easily measure. I said, okay, why should I measure it that and just calculate, which is useful. But really, I think the part that is strong with Monte Carlo is then you can use it to determine things that you cannot measure. One example is that I've shown is KQs. You can use Monte Carlo to determine the KQ, let's say for our chamber design. Of course, if you have a cylindrical chamber farmer, then you would need a different code, probably X++ to simulate that complex geometry of the chamber. But the concept is the same. It's the same concept. But for example, when we look at those in the regions, Monte Carlo was giving you primary total dose and secondary scatter dose. That quantity you can never measure. I don't know an experiment where we can actually separate the primary and the scatter dose completely. This often plays a role when we like in measurement, or actually in the peak scatter factors. We often say, okay, the peak scatter factor is dose in water, Dmax, and then dose in air, replaced with a cap, establishment electron equilibrium. The problem in this measurement is that the cap is now a source of scattering. And the larger the cap, then the more scattering it actually will produce to the chamber. And that's why it's usually not used, this definition of peak scatter factor, measurements for high energies at all. Even when some manufacturers, they say, okay, replace the water cap or plastic cap with aluminum or copper. True, but again, that is still a source of scattering. That does not give you, a good. Usually, there are some problems associated with using these metallic caps. So Monte Carlo, for example, is a way where you can actually determine, let's say, these kind of factors using simulations. So you write the code will register the dose in, let's say, a voxel or in the region. And if a photon was actually scattered or produced somewhere in the phantom, then it will be flagged that this is a scattering photon. And then the dose that, if that photon happens to deposit dose in the region, then that dose will be defined or labeled scatter dose. So in Monte Carlo, one can actually do these things without any issues. I will try with Rakan again. If he cannot, if he has a problem with his mic, then probably I will just end the stream for today, and we'll see. Okay, hello, Mr. Rakan.
يخلوها تزيد في الفاتورة.
Hello, how are you? Mr. Rakan? He left. Probably has a bad connection. Okay, so I was hoping to find someone to join me, but last time it was actually much more fun. We had a friend from South Africa, and I mean, you're probably going to watch this stream. So please come and join me next time on Saturday. Remember, it's on the first Saturday of the month. Okay, so I'm gonna stop now this broadcast, and hopefully we'll see you, inshallah, in a month time. Okay. Okay.